Okay, today we will finish the part we started yesterday by adding a more complete understanding of the proper shader coding. So, um, of the whole process that starts with having some data that we want to visualize in a 3D environment up to the 2D image that we obtain by rendering the 3D scene, we almost went through all the steps except um, those regarding explicitly the rendering pipeline, how to program the rendering pipeline. For doing that, we need to create a program using GLSL. And with this program, we define a set of steps that will tell our GPU how to handle the data that we are sending to it. So this is more or less all the schema of this operation. We have a JavaScript program which resides on the main memory of your machine, usually, that sends some data to the GLSL program, which instead resides on the memory of your GPU, and after a set of steps, we obtain the rendered image that we want to obtain. The first part was the focus of the previous lessons. We created the buffer, we binded it, we send the data to the buffer, enable the communication between the buffer and the GLSL code, then specify how to use those data, and then we see by a drawing call, which draw elements or draw array, the results. But in all our examples, we just copied and pasted some code for the shader part, the obscure part, which will be the focus of this lesson. So the sequence of steps that we need in order to visualize to the image, to create the image that we plan to visualize, because the visualization itself is something extra, meaning that we just reach the point of creating the video buffer. But when this video buffer is visualized, well, it depends on the hardware, and so it's outside this part. But let's say that we need to create the 2D raster of the 3D environment. This is what compose the rendering pipeline, how we can code the rendering pipeline by means of shaders. In the full version of OpenGL, as well as, for example, in DirectX, etc., there are many more steps. Not only a vertex shading step and a fragment shading step. There can be many more shaders, and then means many more steps. But let's focus on those two because are the most important. By itself, a shader is just a little piece of code. It's a small program, an individual program. Small, okay, it's imperfect because it hasn't to be small. It can be large too with respect to other shaders. But it's an individual program that is executed on your GPU, and its purpose is to process the vertices and performs all the rasterization tasks that we want to achieve. So you can see that the client part is not the topic of today's lesson. We just go to the server part, the program that resides on the GPU. Okay. So, of course, shaders are written in GLSL, So let's start with the vertex shader. In the vertex shader, we have all those operations that we want to perform over each of the vertices of our model. Vertex shader operation for each vertex. Typical operations are, for example, the computation of world view projection. You have seen that in order to visualize something with a perspective, we need to pass at least three, well, just one, but in 3D environment we need three matrices. And the multiplication of the values of each vertex for the matrix that we want to use happens per vertex and thus happens inside the vertex shader. Vertex color computation. The last example of last lesson was about coloring the faces of the cube, interpolating the values from vertex to vertex. That computation happens at this level. And we will see one of the methods for an approximation of illumination of a scene. The color of light and then of the point of the surface struck by that light can happen also in the vertex shader if we decide to use the Gouraud method. We will see two methods, the Phong and the Gouraud. The Gouraud, you can think about it as an approximation of the Phong method. It's important to understand that if we need to render triangles that of course have three vertices, the vertex shader is executed three times. That's why we need parallel computing, and that's why we use GPUs for running shaders. Because there are a lot of very similar operations that must happen all at the same time, and we have to collect the results after all those operations. The output of this step is a sort of, let's call it blob, but all the vertices are assembled into the primitive that we have expressed, we have requested in the draw call. If we request triangles, at the end of the vertex shader, we are going to have a collection of triangles. If we ask for lines, we are going to have a collection of lines, and that's it. It depends on the argument passed to the drawing command. Also, clipping and screen coordinates are computed at this step, meaning that you don't have to explicitly calculate if a given mesh is completely inside the frustum, totally outside the frustum, or partially in between. It's something that automatically happens. The vertex shader automatically do that. And also the transformation to screen coordinates of everything we are computing. Something that happens automatically. Then all the primitives are converted in a 2D image that contains information such color and depth, etc. There's the first step of rasterization. All those information are then passed, usually passed, to the next stage of the rendering pipeline, which is specified in the source code inside the fragment shader. At this point, we have a grid that represents just in dimensions the final image, and we want to process each of the pixels inside this grid. We have fragments at this point. A fragment is something like a pixel, a candidate pixel, meaning that we have more informations than required at the end of the pipeline for each of the elements of this grid. For example, we can have the colors of more than one mesh. If we have an object in front of another one in our scene, the color of each of those elements is computed together along with the Z value. When at the end of the pipeline, pixels are sorted using the Z value, possibly maintaining only the value closer to the camera, the other are discarded. But up to that point, which happens inside the fragment shader, we have the information about all the pixels, the candidate pixels at that point. Typical fragment shaders operation are, for example, anti-aliasing, so in order to avoid jagged edges, the depth test, deciding which pixel is going to be maintained for the Z test, the color blending between two different pixels. If the pixel closer to the looker has some sort of alpha value different from 1, so there is a transparency or a semi-transparency, we have to compute which will be the final color, because there are a contribution from the first one and a contribution from the second one. And so we have to decide the final color. The dithering, which is downgrading all the possible shades of a color using only a palette available in that machine. The application of a texture. This is quite important because texturing happens only in fragment shading. We cannot have texturing inside the fragment. Why that? Simply because in fragment shader, in the vertex shaders, the colors along the surface are interpolated. So unless we want to have just an interpolation of colors, we are not going to see the image that we planned to attach over a surface. We need to compute, to project our image over a given face, pixel by pixel. So we have to do that in the fragment shader. Otherwise, we obtain an interpolation of values and not the color that we expect. Also, the color and the light computation, so the color of a surface struck by a light ray, if we compute lining using the Phong method, the Phong algorithm, which is a pixel by pixel computation. While the Gouraud is just I compute the color of a pixel struck at the vertex and I interpolate the results along the edges. In this case, instead, I decide to fully control how the surface behaves to the light. The first operation is quite simple. They can just be enabled by default function of GLSL. The last two must be explicitly programmed because there are too many different variables, so if they cannot, those operations cannot be simply automatized. At the end of the pipeline, we have the image, which is complete and ready to be displayed once the VSync signal tells us that should be sent to the monitor. As I told you, there can be many more steps. For example, there is a geometry shader that can exist between the vertex and the fragment with the task of simplify very complex surfaces, which doesn't happen usually in embedded devices. And since WebGL was taken from the implementation of OpenGL for embedded systems, they decided to discard it. And there are also subsequent post-rendering processing for more complicated visual effects, all the visual effects that can be added after we have the full image assembled. Okay. Of course, we need to send the data that we want to use for the visualization through the different steps of the pipeline. So, for this, there are different types that specify which kind of data we are sending and where we are sending them. We have attributes, uniforms, bearing, and another types that are the textures. After version 3 of full implementation of OpenGL, they changed the type's name. So if you look on the internet, looking for examples, if you see, you will see different names, name clashing of sort. I will go briefly in that, just if you want to make some experiment by your own. So we have attributes, uniform, bearing, and textures. The attributes are those values which changes per vertex. Attributes can be sent only to the vertex shader because of this. Typical attributes, most common, are x, y, z position. They change for each vertex, usually, unless we have two overlapping vertices. Of course, not only x, y, z are the values passed for each vertex. We have seen that we can send more. We can create a more complex vertex format, adding information, as in the case, for example, of the colors. So just x, y, z, we have 12 bytes of data sent for each vertex. That become 24 if we want to express some colors for each vertices. 24 also if we change, instead of having RGB values, we have normal values. And if we add just the UV coordinates in order to display correctly a texture over a mesh, we reach 32 bytes for each vertex. Okay. Uniforms instead are per program variables that are usually constant during program execution. Examples of uniforms are, for example, matrices. I use the same matrices at least once for all the vertices that I want to visualize if we are talking about the world view projection matrix. So that remains for all the vertices. It's true that the next rendering cycle, that matrix may be changed, but for one execution, one full execution of all the pixels of the image, the value remains uniform. It's uniform for all the vertices. They can be passed both to the vertex, both to the fragment. We will see examples about this in order to understand when we need a uniform going to the vertex, when we need it going to the fragment. Uniforms, independently to where you are sending them, or to the fragment, both to the vertex, they start always to your code. They are not values that can be exchanged between the steps. Then there is the texture data, called samplers, which is a special form of uniform used for texturing. Theoretically, you can also send the texture data to vertex shader, but that's very rare, really rarely happen. Okay. Textures are a little bit more complicated, so we are going to see something about them later in this course. And then there are the varying. The varying variables holds the results of something that has been modified inside the vertex shader, but we want to use again that value inside the next stage. We want to use it later in the pipeline. The value that we collect from the vertex shader are, of course, interpolated over a face. Okay, That's more or less just to give you a broad picture about what we are going to do now, what we are going to program. In the specific, a GLSL shader program is just a C-like program. The syntax is more or less the same, not C++, plain C. And if we take a look at the vertex shader that we had inside the code of past lessons, which was kept inside an object called VS, and we improve its readability, that's what we obtain. So, ignoring, of course, the VS, which was just a placeholder and an order, you can see that we have this part here, which is the proper text code. VS was just a way for sending to JavaScript all the strings inside the code. Today we will see another way. So, as you may expect, we have an entry point characterized by a main statement, usually with void parameters. The same is true, of course, for the fragment shader, so we don't replicate the description for it. If we put any variable outside the main cycle, they become, of course, global. And if we are managing attribute varying and uniform, they should be, of course, globals. Otherwise, we cannot send those values to the shader at all. We have a storage qualifier, a variable type, and then a variable name. Storage qualifiers, attribute varying uniform. Variable type is the type of attribute that we are passing. That can be, of course, optional. As I told you, it depends. If you don't put it, they become just simple variables. You could use it to be used in the local scope. Otherwise, they become mean to communicate with the shader. So, storage qualifiers are const. If you want to put a constant read-only inside your code. Attribute, which is the linkage for passing to the vertex shader information about vertices, uniform, and varying. Of course, they are global because otherwise they don't link. Okay. Those instead are the accepted basic variable type, the usual one, the void, boolean, integer, float. The most interesting part are since we don't have structures, we are not going to use structures. They can be coded, but we don't do that. There are some variable type which are very handy for the tasks that we need to perform using WebGL. And these are vectors and matrices, which are used a lot, so we can have a look at them in more detail. Okay, we don't have any new statement, so if we want to declare a vector 4 meaning, of course, a vector of 4 values, vec3 is a vector of 3, vec2, etc. Doesn't exist a vector of 1, of course. Vector 4, for example, the first one, you see that we have simply specify probably a color for that light using and putting inside vec4 the definition of vec4 simply for floating values, and that's it. This is the most straightforward. Direction usually are expressed by vector 3 and UV by vector 2. This is a sort of default. You are not, of course, you can express a direction adding a fourth parameters, but that's a waste of memory. Okay. The interesting thing is that we can extend a vector 2 to a vector 3 simply adding a new inserting in the constructor the shorter vector plus the extra element that we want to create. For example, we have a vector 3 for a light direction. We have a fourth value that we want to add to it. You see in the return that we are creating on flight a vector 4 that is going to have as the first three values the vector 3 and as a fourth value the float number. And this is quite useful. We will see why. We can do also the opposite operation. We can extract values from vectors instead of specifying the index of the value that we want to extract, simply using this kind of notation. So, for example, in light.x or r or s always refers to the first element. Light y, g or t always refers to the second one, and that's it. Also, it's also possible to collect two values. For example, if I write light.xy, I am extracting two values from the vector. Okay, functions. Functions are defined too in a way very similar to C. You have just a return type specified at the very beginning. Of course, it can be void if we have no return statement, just a procedure. Then there is the name followed by the parameters, and of course everything between brackets. You can have local variables. Of course, they exist only inside function. And that's pretty much it for function. One last, let's say, quite important specification is the precision qualifier. Since, again, WebGL implementation started from embedded system implementation of OpenGL, it is assumed that embedded devices have less resources at disposal in terms of memory, in terms of battery, etc. So in order not to waste those resources, it is possible to downgrade a little bit the precision of some of the variables, like floating samples, etc. The precision qualifier, high P, medium P, or low P, can be expressed both before declaring a variable or at the very first row of the shaders, and then it becomes valid for all the code inside that shader. Here you see that it is expressed in front of each variable, affecting only it, of instead the precision of all in the shader. Vertex shader do have a default. Instead, fragment shader doesn't have a default precision for its variable. So the first row of a fragment shader must have a precision statement, otherwise it won't compile, and at the exam it is an error if you don't detect, for example, that you don't write it or you don't detect in already written shaders that it missed. Okay. There are a couple of special variables, which are of course global, that are used by WebGL to communicate intermediate results automatically from one step to another one. They are fundamental, otherwise you don't see anything. And in the vertex shader code, this is GL position, which is usually the last statement of the vertex shader. Inside GL underscore position, the final values defining a vertex position in the space are collected. So that position is where my vertex is going to be placed. The same thing exists in the fragment shader, and it is GL underscore frag color. That's the final color that we want for a given pixel. Those two special variables must always be present in the code, otherwise nothing works. It's interesting to note that GL frag color is deprecated in the full web OpenGL implementation, because there is no way to tell that the fragment shader is the last stage of the rendering pipeline using OpenGL full version. You may have more steps later, so that's it. Once we have the code, we are satisfied with our code, we must compile and link, of course, all of this. This is done using some function, again in the client code. And that's another part in the obscure part that we used the other time. We have, first of all, a create shader, gl.create shader, which allocate, again on the GPU memory, a buffer containing, which can contain the code for both a vertex or a fragment shader. The only enumerator that works are vertex underscore shader, fragment underscore shader. Then we put inside that container the shader's code. So shader source put inside the shader object that we just created the string containing the source code. At this point we just compile everything. Of course, a lot of error and mistakes can happen here, and then they have to be intercepted explicitly, or they go silent. You don't see anything. Simply, you don't see anything on your browser, and you guess for a lot of time why and where is the error. So we will see how to add some error catching, which works, let's say, 50% of time, not all that precise. But now we have two partial programs, not yet the full pipeline. To create the full pipeline, we have to create program. GL create programs allocate the portion of memory for the full pipeline. Then we attach, we put inside this program object the partial compilation code, the objects, basically, of the previous compilation stage. And then we link everything together along also all the function contained in the implementation itself. We have a program that can be used. And if you remember, the first row after the part that we copy is GL use program with the handle to the program compiled. So before a break, I just want to give you a summary of all the workflow, which I understand is very, it's, let's say, hard to understand at the first impact, but once you start coding, it's more difficult to explain it than to do it. So let's say that we have a client application, we have some 3D object that we want to visualize, we have them in some format, so we can assess the data that composes those objects, and then we have a working vertex shader and fragment shader code. The first thing that we do is to put all the data about the object inside a buffer in the GPU memory. we put all the data that we need to visualize there, the data about the geometry. Then we compile the shader, obtaining on the GPU memory a compiled shader program. The compiled shader program is made by a vertex shader part, a fragment shader part, and there are attribute uniforms and also textures waiting to receive data. That's why we get some handles to those variables, and we obtain their location, attribute location, VS uniform location, FS uniforms location. You see that the varying is not something that we handle from the client code. It's something that is only inside the shader. It's for the shaders only. Then all the data that we have are sent to the shaders. They can be sent directly from the client code. We have matrices. We just feed the matrices. We don't have to buffer the matrices anywhere on the GPU memory. Or if we have buffered some of the data, those about vertices and normals, then we allow communication between the buffered data and the proper location where they are expected. So in the end, the vertex shader is able to compute all its per vertex computation, and fragment shader, using those partial results, complete the computation of the color of a portion of the image. Okay. If you have questions, please ask.